Hi, good morning. Welcome to the section on site performance efficient evaluation and decision. I'm Kingsum Chow from Alibaba. Along with me is Zhihao Chang from Zhejiang University. Together we work on a project called Speed. The need for speed is about how to get the reliable performance data from the data center and how to detect performance difference in a large number of applications running on a large number of servers. Welcome to our talk. The data and methodology we are sharing today is only for illustration only. This is not real data in the data center, but we believe the data we are sharing here is also going to be useful for any of you that is going to take the methodology to try it out with your own data. We're going to focus on two aspects of performance analysis at scale in the data center. The first one is about some of the performance metrics might be misleading. We're going to point out one of them, that is CPU utilization. The second topic is about when we evaluate performance at scale, sometimes the conclusion can be misleading. And we're going to talk about how to address that and some of the tools you can download and play with. First, about speed. In a very large data center or a group of data centers, we have lots of applications running on lots of servers. When we need to optimize the system, we are looking at applying a change, and that change can affect a lot of server applications and also a lot of hardware systems. The challenge is how do we evaluate that? So we have many changes we would like to consider, and we have many applications that are running together that need to be evaluated, and we have many systems that can be applied the change or not. So how do we do that? First, let's talk about the data collection process. In particular, one of the common performance metric that is called CPU utilization. Let's use the most common CPU utilization definition. That means you pull the CPU utilization from your tool, like running SAR or VMstat on Linux, or activity monitor from Mac, or Windows Task Manager. They all provide some kind of CPU utilization. On the system, you will see something like between 0 to 100% CPU utilization. And what does that kind of CPU utilization mean? Does it mean that you are using that percentage of capacity of the CPU you have on your system? So let's pose this question. A data center that has a CPU utilization of 50% running a certain amount of applications on a certain number of hardware. And let's say we assume there's no software scaling or no interference problems. Does it mean that we can reduce the number of servers by half? Again, I want to point out that we are assuming there's no hardware or software problems. The only question we are asking here is, does the performance metric CPU utilization mean what most people think it means? Let's take a look at Intel server. Right now, Intel servers are by far the most popular servers running in the data center. Intel servers have some cool technologies. For example, one of them is hyper-threading. Let's talk about what hyper-threading means here. On this figure, without hyper-threading, one thread is running on one core. That is the first half of the figure. When you turn on hyper-threading, two software threads are running on two hardware threads. They're sharing the same core. In other words, hyperthreading enables the core to appear as two different CPUs to the server. So here we can take a look at some of the possible performance data you can get with hyperthreading turned on. In the top figure there, we have two threads running on two cores of a server, and each core is running one thread because we have not turned on hyperthreading. 100% CPU utilization in such a case means both threads are busy, both cores are busy. Let's take a look at the bottom about what happens when hyperthreading is turned on. In the lower left chart there, with hyperthreading turned on, in this scenario, you have one thread being active in each core. Core 0 has thread 0 busy all the time, and core 1 has thread 0, thread 10 busy all the time. In this case, 2 out of the 4 logical CPUs are busy all the time. That means the system is 50% busy or 50% utilized. In the scenario in the lower right corner, we still have 2 cores with 2 threads each as a result of hyperthreading. In this scenario, you have 2 hardware threads that are sharing the core 0, and both of the threads are busy. In the other core, core 1, both the threads are not busy. In this figure, again, only 2 threads out of 4 threads are busy. So the CPU utilization is also 50%. So we have seen that 50% CPU utilization can mean 2 different things earlier. In fact, those are the 2 extreme cases. There are many, many cases in between that may be measured using this kind of CPU utilization. Let's run an experiment to see exactly what that means in our performance analysis. We took an Intel system with 2 sockets, 16 cores per socket, hyperthreading turned on. 2 times 16 times 2, that means we have 64 logical CPUs running on the system. We picked a benchmark called SPECjbb 2005. The reason we picked this benchmark is we can run with each warehouse, but with each software thread running on one logical CPU. We can pin the logical CPU to 32 threads running on different cores, or we can pin it to 64 threads running on all logical CPUs. After we run this experiment, we obtain the throughput. That means the total amount of work done running in each configuration. In the left figure, the blue bars refer to the configuration. We are running just 32 threads out of 64 logical CPUs. And in this scenario, we are running 1 logical CPU per core. So each core is busy doing something. However, because we are only running 32 logical CPUs out of 64, as you can see on the figure in the top right corner there, the CPU utilization is reported to be 50%, as we expected, because we are running 32 logical CPUs out of 64. But you need to pay attention to the figure on the left that the total amount of work done between the configuration in the blue and the configuration in the red, the total throughput is about the same. When you look at the top right corner, the CPU utilization of running at 64 logical CPU is 100%. So we are looking at the situation that you can use 50% of the CPU utilization, that is the blue chart, or 100% of the CPU utilization, that is the red chart, and surprisingly, you are doing about the same amount of work. So the question is really, does CPU utilization capture the notion of how much CPU capacity is being used? We are not saying that hyper-threading is bad. We're saying hyper-threading indeed brings performance improvement for a lot of applications. All we are saying here is we need to be very careful when you're looking at the CPU performance characteristics with hyper-threading turned on. We need to be able to think about the CPU utilization in different scenarios, especially how the utilization is distributed across all the logical CPUs. With that, let's move on to performance estimation at scale. When we are running a large number of applications on a large number of servers, we would like to have a unified way to measure the efficiency of software. The efficiency of all software can be summarized in a simple way. While this simple way may not capture 100% of the software applications, we believe that it is reasonable enough so we can compare the effectiveness across different applications and across different hardware configurations as well. We define resource usage effectiveness, RUE, as resource usage per work done. Resource usage can be measured using CPU utilization, for example. Earlier, we talked about CPU utilization can be misleading if you just use the overall number. However, the CPU utilization might be more meaningful if you break it down to individual cores or individual logical CPUs. We adjusted the CPU utilization with the understanding we have just shared, and we divide that by work done. That means if a software can use less resource doing the same amount of work, it is more effective. And that can be captured by the equation we are showing on this slide. We are comparing two configurations. The configuration can be a hardware change or a software change. For example, changing the NUMA configuration of the hardware, or changing the CAD design of the hardware, or changing the software may refer to upgrading the OS parameters or upgrading the runtime JVM parameters, etc. When you apply such a change to a large number of applications, for each of them, we can compute resource usage effectiveness defined earlier. The speed up is defined as the RUE of the first configuration divided by the RUE of the second configuration. So when you get a higher speed up, it is better. When you get a lower speed up, that means the change may bring in a poorer performance. By using this equation, we can apply that to a large scale of software running on a lot of hardware. Now, how do we do that? Remember, in the data center, there are many people running many different applications. Each of them has the objective of optimizing their application. Maybe they would like to use more hardware. Maybe they want to focus on parameters that are specific for them. So there are many reasons that different parameters can be applied to these different applications because they are owned by different departments. What we need is to unify the performance metric across a lot of applications in the data center. The task is very daunting. Fortunately, there is the law of large numbers. What that means is when you have a large number of instances running in the data center, even if there is a small error due to, for example, different applications are packed together, or different applications are sharing the cores, or different applications are sharing the systems. There are lots of varieties when you are placing a large number of software applications on a large number of servers. When you have a large number of instances of each application and large number of instances of hardware systems, we can try to use the average behavior of really large numbers to help us to detect if a change is helpful. For example, in order to test a new feature, we can turn on just 1% of the instances of the application running with a new configuration and compare that with 99% of the instances running on the old configuration. We're not changing any way the deployments are being done. We are not changing any way the application is being launched. That way, we can collaborate with a lot of teams in the data center. And so far as we have a large number of samples, we will be able to evaluate the performance difference. So here is a figure that illustrates what we are doing. We reduce the number of machines and the number of applications drastically to illustrate what we are doing. On the left, we have 4 machines and 4 applications. And just by chance, they are deployed on these 4 machines in different ways. Some of the machines have more resources, like machine 4. Some of the machines have less resources, like machine 1, 2, and 3. Sometimes the application may need more resources, like app 3 running on machine 2 and 3. Sometimes they can use fewer resources, like machine 2 running on app 2 running on machine 1. Because changing the configuration for all the applications can be very costly. So one way to evaluate the performance impact is to change a very small number of configurations. In this scenario, we are just illustrating using the figure on the right. We are just changing the configuration of machine 1. That means when you're looking at the figure on the right, you have applications 1 running on machines 2 and 4, the old configuration, and the application 1 is running on machine 1 with the new configuration. You can see that we are comparing the new configuration and the old configuration at the same time. So this is interesting because if the flow of the transactions are changing during the time we are estimating the performance difference, we get a change in the user behavior on both the systems. This is very helpful for the performance evaluation because we just rely on the load balancer to work as usual to distribute the request as usual for our comparison. So here is an example of the data. Again, this is just for illustration. This is not real data. When we launch a test of a large number of application instances, in configuration 1, we get the rule of 885. In configuration 2, we got the rule of 815. And remember, the lower the rule value, the better the performance. And that is indicated by the speed up on the right. So it looks like by applying this change from configuration 1 to configuration 2, we get a speed up of 1.09. This looks very good. Should we apply that? Because we have a large number of instances, and because the applications can be running in different phases and different modes, we have a chance to take a look at the breakdown of the application. For this specific application, it can be broken down into 3 kinds of behavior. For simplicity, we call them groups 1, 2, and 3. Let's take a look at the data here. The application group 1 is handling 50.1% of the instances. In group 1, in config 1, you have a rule value of 1289. In config 2, you have a rule value of 1484. That means within all the instances in group 1, the speed up is actually going down 0.87 as a result of dividing 1289 by 1484. Let's pick a second group. 31.5% of the instances running in the group 2 scenario. The rule of that is 428 versus the new configurations of 434. The numbers are very similar, but it still reflects a speed up of just 0.99. That means the performance actually goes down. Let's take a look at group 3. The number of app instances is about 17.4% with a rule value of 550. And the rule increases to 655 in configuration 2. That means for this configuration change, the speed up is just 0.84. Now we are seeing something very surprising. When you look at the total behavior of running all the applications, the speed up is 1.09. That is positive. We almost want to apply the change. However, when you divide the data into 3 different groups that all belong to the same app group, each of them shows a negative speed up. That means the performance gets worse within each category. So this kind of phenomenon is called the Simpson's paradox. A trend appears in several different groups of the data. In our case, groups 1, 2, and 3. But it reverses when these groups are combined together. And this is the kind of the paradox, and this is the kind of scenario we need to check for when we are doing performance analysis at large scale. We cannot simply look at the overall summary of the performance data. We need to look at the individual groups as well. So you may ask, why would that happen? Let's illustrate that with a simple animation here. We are using the data we described earlier, and we plot them using resource utilization divided by work done. That means each of the data point can be represented by a vector and arrow, where the y-axis is resource utilization, the x-axis is work done. So RUE is a slope, resource utilization by work done. From this chart here, we have 3 pairs of arrows. The first pair are the 2 lines that are on the top, and the second pair are the 2 lines in the middle, the third pair are the 2 lines at the bottom. The overall behavior of these changes is the result of acting the vectors in the adding the vectors in the green and adding the vectors in the blue. Let's see how that works. So when we add the vectors in the blue, essentially, we have this line that is the diagonal line joining the three other vectors. And we can do the same with adding the vectors of the green. Notice that initially, all the green vectors are higher than the blue vectors. But when you add them up, the resulting green vector, this line, has a lower slope than the blue line. So the reverse change can be expressed as the sum of the vectors by looking at the difference in the slopes. This is kind of vaccinating, and it is something that is worth checking for when you are analyzing performance data at scale. If you like to try it out, there are many GitHub packages you can download to do this kind of analysis. I'm just sharing 4 of them I've looked at. They have different approaches to detect Simpson's paradox in the data. So let me summarize today's talk. CPU utilization can be a little bit more complicated than it looks. We need to be very careful by looking at the per logical CPU, per core, and per system CPU utilization. Once you can account for the CPU utilization, and if you decide to look at the performance difference between resource usage and the software work done, when you're looking at the data at large scale, be careful about the Simpson's paradox. You do have to compare the overall performance difference with the individual group difference. Okay, I hope you liked today's talk. Thank you so much. See you next time.